Hello and welcome back. So let's do a summary of what we have done so far, but also let's talk about restarting capabilities. So at this point, I hope you understand better this workflow that we have here. It's very important to understand this, and if still things are not clear to you, just try to repeat this case because in this case we're doing something a little bit different from the very easy case of the cavity here where we have a little bit more complex workflow where we're putting different applications. So remember that you have Dakota that is just synchronizing everything, orchestrating everything, and it's going to generate some parameter files, but also it's going to get some results on outputs to keep looping. So here you have your input filter, output filter, and then you enter into the level of the simulation control script. So here's where you put all those sequential instructions to run your case, and that's all. So here you can basically, in theory, link many applications while they can take values using a command line interface or scripts, but also using a GUI. It's a little bit more complex, but it can be done. So you can link everything and you keep looping. So this is a big picture now talking about Dakota, but then if we go into details, it's also important to understand what is happening here, these files that we're moving here. So we have templates, so you need to identify what will be your parametrical file. So it can be anything that you have in your case directory. So identify that. Remember that we're using as delimiter to do that substitution. That will be that input filter. We're using curly braces and the name of the variable that most of the time it doesn't give you any problem with your files or whatever you have already, the application library that you're working. But also you have a case base. That case base needs to be something that you know it is working. It is a starting point where you have defined numerics, also the predefined level of convergence, or how long are you going to iterate, and so on. And here again, we go into the simulation control script where you give all those sequential instructions. And here's just a lot of, sometimes it can be easy, sometimes will be a little bit tricky just to uh, translate the output of the application to the format that Dakota likes. Now, this will be the results out that will get it back here in your loop, and Dakota is going to generate patterns in that you're going to give here. So these are your filters. So understand this, and as soon as you understand this, I think you are in your way to master how to do to how to implement automatic loops, but also how to do optimization and so on. And then just you have only one input file in Dakota. I know the user is extension that in. Okay, it doesn't matter in Linux, by the way, that extension, but yeah. Let's skip it. And here you define your problem. So understand what you're doing, define your problem. And for our case, we are going to use always the fork interface. There are different levels. If you want to know the different levels, always you have the documentation. So this is the summary that we have done. And here in this case that we just run, and let's go back here that we will run in this case. And with the previous one, we run, if I were to recall the video, we use this method. Now I rerun the case using another method. So remember that there are many methods. So here we're working now in the level of gradient-based optimizations and actions, and I want to stress that you have documentation, which is very good. So remember that you want to know those methods, you need to get familiar with the theory, the methods that are implemented. So in theory, you can use anything because you have the methods that comes with Dakota, but you can link Dakota with Python, whatever. So you have basically infinite resources. So this is the one that we used previously. So this method. So now I rerun using this one, the Q Newton. There is a quasi Newton optimization method. So it have a very good convergence rate. And also you have Newton method. So knowing the theory, okay, for these Newton methods, you need to compute Haitians. So Haitians are let's say Jacobians, if you're familiar with that. So the second order derivative. So you need more information. You need to compute those numerical Hessians. So it will be a little bit more expensive, but the best convergence rate is a quadratic convergence Newton method. So also, if your function evaluation is inexpensive, you can try to implement this. Just to stress that in that case, that is, you want to use a method that needs Hessians. See that here, no Hessians. But if you use that one, likely if you don't give the information that how you compute the Hessians, likely Dakota will complain. And very similar to what happens in OpenFOAM, that when you're missing a keyboard or using the wrong keyboard, it's going to tell you, okay, you need to, this doesn't exist, this is the wrong keyboard, I don't recognize this, or you are missing this keyboard. These are the options that you have available. But the way to avoid that is knowing your theory, okay? So spend some time what you're doing and identify your variable. So that's what I want to talk about here. Do that small summary, but also let me address something in this case, and let me go back here because this is our optimization loop, and I just want to spend some words here in Salome tool. So Salome, and let me show you, if you haven't seen Salome, it is this. If you are using our virtual machine, I already have it installed there. By the way, let me go and show you that you have the website. I already mentioned a little bit that it used to be a terrible tool. Like 10 years ago, it was really complicated to use. It worked, but not very user friendly. But now it's getting much better, and I think it worth giving a try and try to use it. It still is a little bit tricky to do cat. Here you can do cat mesh and everything, so it's a little bit tricky, but I think it's getting there. So if you don't have things too complex, give it a try. So this is a graphical user interface, whatever, and basically here when I have this Python script in this case, and let me go back. So you go to my case base, I put here this Python script. So this one was generated here using the graphical user interface. So first you generate the geometry, and then after you do whatever you want to do, you have this action that is dump study, and you can save your script. And then if I want to load that script, here I have it. And when I load the script, it will read all the instructions. So here's giving an error. So honestly, I need to update this script. It's a little bit old, so no structure. So this error that is given here at the end doesn't matter. Okay, but yeah, I need to read it. So this is what when I mentioned that previous versions, it was having problems because it was opening all those TCP, UDP ports, whatever. So this is a way to kill those ports. But if you want, you can comment these instructions, and then you're not going to have, or likely you're not going to have any more that error. So let me do it here, and this is Python, so just the comments or hashtag number in there. So let me comment those there, and let me reread here, load the script. And sorry that the text is very small, but yeah, this is the main screen configuration, and see that you don't have it anymore. Okay, so yeah, I need to update things. So yeah, here I asked to the community, somebody wants to help, just please update stuff, but quite busy. So a brief introduction here. This is a complete video just to show you. So here you have the geometry, so see that you access your geometry, and also you have all the mesh and everything. So let me see here where I put that one, and actually let me remember this because I haven't opened this case in a while. Actually, I haven't opened Salome in a while. So see that here we have the case, the BCA points. If you open the file, you will see what is happening there. And this is your geometry. You create it here. You can name, what is cool about Salome also, you can name the inlets, outlets, profile, and everything. You give names. So yeah, I think I will do a video about this. And then here, when you move, you have the meshing. So it's a little bit tricky also how you set up the mesh, because you need to put algorithms and so on, so that select boundaries, but it's quite handy. You can do it, works very well for boundary layers, so you don't have any more the problem that is snappy, which is not a problem. Is you know how to use snappy, you can control that. And now if I move here to the meshing tab, see that you have your mesh there. And here we do an extrusion. Remember that in OpenFOAM you need to have that extrusion, so we can do it here. And there you go, you have that mesh. And yeah, just talking that maybe it would be a good idea to update this one because yeah, I would like to add the boundary layer. So yeah, I have time, and well, if the community asks, I will do that. Otherwise, yeah, I will not do it. Or if someone want to help me, just feel free. So this is just to show you this other tool. Give it a try, or you can do the tool of your preference, so it's up to you. And let me just put those comments. I need to recheck as well that stuff that I say that killing the pores or maybe, but I will leave it open. So that's all that I want to show you. So we have the script there. And now what I want to talk about is restarting capabilities, because it might happen that you are running the simulation and usually if you deploy this one in a HPC center in a cluster, usually you have a time limitation after 24 hours or whatever, it will stop. So it's not anymore fault tolerant your loop. So you want to have things fault tolerant, and this is the idea of having a restart file where you are saving all your sensitivities. So that restart file is always safe. I don't see any reason not to save that. So you need to disable, but by default when you launch Dakota, you always save that information, and it is this file, Dakota RST. Okay, you have all the restart information there. So let's say that imagine that I was running this case and the case crashed at 16 iterations. So let me erase those iterations manually. Okay, I erase everything. So you need to restart any more from scratch. You can restart from 16. Usually the standard practice, at least for me, will be restart from 15 or 14 because it might happen that this information might be corrupted. You never know, but also you need to check that one. But for me, it's a standard practice and it's recommended to go one or two, three, four iterations now before to do the restarting because this might be corrupted depending of the concurrency that you were using. So this is it. And now how do we start? Because we already have all the sensitivities here, the gradings, that information is saved in that restart file. So remember that we have documentation. Always I recommend you look at the documentation. So let me look here. We can look for restart. And you have here restarting Dakota, and you have a lot of information here. So basically writing, as I mentioned, is writing by default, but also you can change the name and so on. But what interesting here, reading restart file. Okay, so we can use this one or the short one -r, and you can read the information that you have it there. So let me go here and let's first read what we have in that file. So let me go there. Okay, so okay, no, okay. So I want to partially read. Now this one will read everything and it will go to the latest record that you have there. But we want to do a partial reading, so we are going to relaunch the case, but also I want to, okay, to read that restart, and then I want to start from a given record. So this number that you have here, you have an explanation, represents the function evaluation, and then it's recommended to save the new files with a new name, okay? So let's do that to show you that Dakota, and you go the name just to relaunch the case from that file. Later we're going to see the information there, and we want to -s, and look at that. Oops, let me type there. So Dakota minus Dakota, bam, 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 bam. Okay, okay, bum. Partially read -s. Okay, Dakota -r. So Dakota case E -r, okay, the file -s, and I want to start. So here our last record is 16. Let's say that I want to go to 14 and I want to save with a new name. So let me say that 1RST. Okay, so basically following this standard practice. If you read this, you will see that also it is a standard practice recommended by the developers, and I have to say that any optimization tool it would recommend you to follow this standard practice. So here what we're doing, imagine that your case crashed or you for whatever reason, a power failure, it crashed, you want to restart. So this is how you can proceed. It's also interesting that you can stop the case. So to stop the case is just a brutal Control C or just kill the process, and you can change the parameters. So you can start running the case, I don't know, using some variables, and then you want to change that. So it's perfectly valid. It can be done. However, it's not recommended. So for instance, you can start using this method and then you can change to another method. It can be done. There is no problem. It's not recommended because they use different algorithms, different ways to compute sensitivity. So the solution might take longer, or you might converge to a optimal solution. It's not the global optimal one. So be careful about that. It's not recommended, but in theory it can be done. You can change everything that you have there. So see that we have this. Also recommend you to save the log file. So usually I put it here, so you can go here and you can save those. So just to keep a good trace of what is happening. And this is it. So basically what you're doing, read the case. Remember that you can change that case. I don't recommend you to do it, but it's up to you. You can experiment. We want to read this specific restart file. It is always save, then -s. I want to start from this function evaluation and then save with a new name and then save the standard log file. So let me go here and launch this and see that it is starting from that case and it's launching everything. So as you check here, you will see that you have all the function evaluations. You are not starting from scratch. So this is the restart capabilities and the failure capturing. You know, it might happen that you have an error, and in that case, it will stop. You can go look at your case and then restart, change something. So that failure capturing also is related. I already mentioned that I put in my case, I put this script just to be sure that you have the results out and so on. But there are different ways to do it. It is up to you. It's your logic. But in Dakota also they put that function as well there. So I think it would be like recover or failure. Let me go failure capturing. Oh, yeah, failure capturing there. Simulation failure capturing, and you have everything, how to proceed, some standard practices, the different types. So just read it here. So this is something that is also relative new, you know. So it wasn't there in a few versions back, you know. I think it was added like in 6.17, 18. I don't recall well. And I check it. I test it with some cases, and it works very well. But let's say that for me this works. So if it is not broken, I don't see any reason to fix it. But it can be a good idea just to use what is distributed with Dakota. It works very well. No, it does pretty much whatever you do in your own script. So I put my scripts, and I have way more complex. So this is the simplest one, but I have things that are way more complex. So basically, now that complexity goes that usually when you're using the grading method, you discourage the algorithm to search in the same point where it crashed. Now, so if it crashed in, let's say, in 1111, okay, you are going to discourage that the algorithm to search there, so you move somewhere else, or you need to look at your data. So you put some logic there. It's not black magic, it's just common sense. So say that we run the case, and here we have the solution, and we can interrogate the output file, the standard out there, and see that we have exactly the same result. So this is the optimal value, this is the value, and your best function evaluation, you have it there in 31, and then you can do your post-processing. So this is a very important part. So get familiar with restarting cases, because very often might happen that your simulations are going to crash, and you need to restart from scratch. You can restart from that trace that you have, and this is very important. To be able to do this also, you need most of the time, not necessarily because you have all the sensitivities here, but in some cases it might be necessary to have the trace of this folder. So that's why also I save the folders. Also, there is some practice that some people likes to accelerate convergence. The people likes to kind of map the solution from previous cases to the next one to accelerate the convergence. Depends in the case. Sometimes it can accelerate, sometimes it doesn't help much. So I leave it to you to test that approach. But in my personal experience, you don't gain much, and sometimes you can slow down your convergence, but you need to test it. Okay, but the idea is like, for instance, you start work there one and work there two, it will be quite similar to work there one. Okay, if it is not similar, it makes no sense do the map. So basically you do here whatever you're going to do here, you map the solution for here and so on. Okay, so sometimes work, and usually it works when these sequential evaluations, they are closely related. But if you go and do design space exploration, it might happen that whatever you have in World 3 is completely different from whatever you have in World 2. So it makes no sense mapping, because likely the solution will be very different. So it's up to you. I don't want to confuse you at a higher level. And finally, I want to also to interrogate this file. So see that we have Dakota RST and then the new one, but there is also another utility that is, oh, let me go here, Dakota util, and let me go. Okay, so that utility just to interrogate, yeah, yeah. So let me go, bam, 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 bam. So I have Dakota. So yeah, this a different one. Okay, Dakota restart util. It's this one. Bam, bam, bam. Let me go. So this one we can use it to interrogate the file. So as you see here, always you have the documentation. So see that, for instance, you want to print the information that you have in that file, just simply go like that. Put it there. And it's printing all your information. So as I mentioned, that all the trace, everything that you are doing, it is safe here. So you have all the sensitivities, everything. So Dakota will know what are function evaluations, what are gradients, and so on. So see that you have it here. So at any point you want to see that record, you can access that. You can even erase a specific record. So as you go here, you see that you will have many options. You can move from one file to the other. You can output that to another format. You can modify these files and so on. Okay, so for instance, it might happen in some cases that you can have corrupted data in that file. So you have here the option how to do it, and you can remove a specific records information. You have to be very careful about that, because unless you are absolutely sure that you have corrupted data, I don't recommend you to erase, because you are messing around with that data, so you can damage some grading evaluation, some sensitivity that you have in this file. So at this point, I think we cover all the basics in a little bit more complex case coupling interfaces. So just to repeat you to repeat here what you need to do at this point. Uh, please get familiar with this workflow, how things work. Okay, so it's very important to understand this concept, the input and output filter. So just to repeat here, the input filter will be Dakota. As you go into any directory, Dakota will generate these patterns in. So this is information generated by Dakota. And here you have the design variables. Remember that also you need to formulate your problem. So you have these design variables. And this design variable somehow needs to be substituted in your black box utility. In our application, our black box utility will be this Python script in this template file. Remember that you're going to have there this curly brace x1, x2, x3. So the prep utility automatically is going to do the substitution here. That will be this file here. And see that now you are substituting all those variables, and then you are ready to go. So if you can reading and everything is done in the simulator script that I have it here outside. So simulator script, and you will have all your sequential steps here. Okay, so as soon as you enter in this simulator script, and according how you define the problem, and usually I recommend you to define your problem just to save always this work dir and save the work directory. You are inside those work directories, and basically what you need to do is just move files. So here you are doing the substitution. You can substitute that, do that substitution in multiple files. There is no limit. Then run your sequential. This is the analysis, the sequential steps as if you were running OpenFOAM from your terminal. So for instance, you want to run now OpenFOAM in parallel. Just go here, decompose par, then MPI run minus MP2, whatever, phone run minus parallel, and reconstruct par. You work exactly in the same way. No need to mention that you need to have the computational resources, so be careful about that. And also double check always. So if you're running locally, it is inexpensive, but when you move to a cluster, if you make a mistake in your script and you're missing a file, again you need to go into queue. So always double check all your case base, your scripts, everything that you don't have a missing file. So for instance, in this case, if I want to run in parallel, and if I put there the compose part, see that I'm missing the compose part, so it's going to complain and you're wasting that time. So always double check that everything is ready to run before submitting that into the queue. If you're using queue systems, you are not using that, okay, it's just as you go, you're going to find the errors. So I think I have addressed everything. So uh, all the concepts here, and this is great. So for this point, hope that you have a better grip of what is going on. So in the next cases, I'm not going to spend so much time to explain this theory. I'm going to assume that you now master that, or kind of you know what is happening, and we're going to move into more elaborated cases and test new techniques. So thank you for your attention. See you next time. Bye.